In previous lecture, I already discussed open addressing. In open addressing, every key will be inside the hash table. There are no chaining concept. In open addressing, collisions are resolved by three techniques. First is linear probing, then quadratic probing, then double hashing. I already discussed linear probing in previous lecture. Today I will discuss quadratic probing and double hashing. In linear probing, hash function is h of k equals to h dash k plus I mod m. H dash k is the first hash value and I can range from 0 to m minus 1. M is the hash table size. In quadratic probing, hash function is h of ki equals to h dash k plus c1I plus c2I square mod m. If you remember, quadratic equation is in the format ax square plus bx plus c equals to 0. Here this I equals to x. So c2I square plus c1I plus h dash k. Due to this format, the name is quadratic probing. Here C1 and C2 are some positive constant. I range from 0 till m minus 1 and h dash k is the auxiliary hash function. The initial position is t of h dash k and later position probed are offset by the amount that depends on quadratic manner on probe number I. So whatever we'll find by this hash function, that will be our next probe sequence. C1, C2 and M should be constant. Suppose we have two keys K1 and K2. If for both first probe number or first hash value is 1, then its next hash value will be suppose 3 for both. Then its next hash value will be let 8 for both. So if two keys have the same initial probe position, then their probe sequence are same. Since h of k10 equals to h of k20 implies h of k1I equals to h of k2I. So both keys are following same probe sequence. Suppose k1 is inserted in the hash table, then for k2 there will be no place as k1 is already filled in that sequence. So in quadratic probing, there may be situation arise that will not get slot for a key. There will be empty slot but will not get place for a key. So it's not guaranteed that we can successfully insert a key into the hash table. And this problem known as secondary clustering. Linear probing suffer from primary clustering where multiple keys can gather in one place, and quadratic probing suffer from secondary clustering. Two keys may follow the same sequence. Next is double hashing. For double hashing, hash function is h of ki equals to h1k plus I multiplication h2k whole mod m. Due to these two hash function, name is double hashing. Both h1 and h2 are the auxiliary hash function and the value of h2k must be relatively prime to hash table size m. And m can be either power of 2 or prime. So one example is h1k equals to k mod m and h2k equals to 1 plus k mod m dash. This m dash is slightly less than m. If m equals to 10, then m dash can be 9. When m is prime or power of 2, double hashing is better than linear and quadratic probing. Linear probing suffer from primary clustering, quadratic probing suffer from secondary clustering, whereas if m is prime or power of 2, double hashing is better than these two. It doesn't suffer from primary clustering or secondary clustering. Next, analysis of open address hashing. I already analyzed chaining. In case of chaining, alpha is our load factor equals to n by m, and this alpha can be less than, greater than, and equals to 1. But in case of open address hashing, alpha is strictly less than equals to 1. n divide m less than equals to 1 means n should be less than equals to m. So number of keys should be less than equals to table size. And we assume that we are using uniform hashing. Uniform hashing is a hypothetical concept where we uniformly distribute all keys in the hash table. So it assumes that the sequence are h of k0, then h of k1, h of k m minus 1 for insertion and searching the key k. There are two theorems for successful search and unsuccessful search. First theorem, given an open address hash table with load factor alpha equals to n divide m less than 1, the expected number of probes in an unsuccessful search is at most 1 divide 1 minus alpha, assuming uniform hashing. So expected number of probes in an unsuccessful search is at most 1 divide 1 minus alpha. So maximum will search 1 divide 1 minus alpha time. If by this we are not getting, then we'll declare it's unsuccessful. The key is absent. There is a corollary based on this. So inserting an element into an open address hash table with load factor alpha requires at most 1 divide 1 minus alpha probe on average, assuming uniform hashing. So for insertion and for searching, at most 1 divide 1 minus alpha probe will consider. Next theorem is for successful search. Given an open address hash table with load factor alpha less than 1, the expected number of probe in a successful search is at most 1 divide alpha ln 1 divide 1 minus alpha. Assuming uniform hashing and assuming that each key in the table is equally likely to be searched for. So the expected number of probe in a successful search is at most 1 divide alpha ln 1 divide 1 minus alpha. The proofs of these two theorems are present in Coleman book. You can refer that. I am not explaining it. In today's lecture, I discussed quadratic probing and double hashing. In next lecture, I will discuss one example of linear probing, quadratic probing and double hashing. If this lecture is helpful for you, please like, share and subscribe. Thank you.